Assalamualaikum and a very good day to everyone. My name is Nur Alili Afifi and I will be presenting the introduction to our experiment entitled Application of Bernoulli Equation. Bernoulli equation is a fundamental principle in hydraulic that describes the conservation of mechanical energy in a steady incompressible fluid flow. According to the NASA Green Research Center, the equation explains how pressure, velocity, and elevation are related while the total mechanical energy of the fluid remains constant under ideal flow conditions. Engineering liberty text further explains that the total energy of a flowing fluid consists of three components, which is pressure head, velocity head, and elevation head. These energy components change along the flow, but the total remains constant provided the flow is steady and friction losses are negligible. In addition, Encyclopedia Britannica states that Bernoulli theorem is widely applied in hydraulic and civil engineering, particularly in design and analysis of pipelines, water supply system, pumping station, and flow measurement devices. The problem statement in this experiment is that pressure and velocity vary as water flow through a pipe with different cross-sectional areas. Therefore, experimental verification is necessary to determine whether the measured pressure head, velocity head, and the total head agree with the theoretical prediction of Bernoulli equation. Hence, the objective of the experiment is to verify Bernoulli's principle when applied to the steady flow of water.
Hi, my name is Alia and I will be explaining the basic concept. For this lab, we are evaluating Bernoulli principle, which is simply the law of conservation of energy to the flowing fluid. It states that an increase in fluid velocity happens simultaneously with a decrease in static pressure. In mathematically, we express this total energy as total head, which combine pressure head, velocity head, and elevation head into a constant value along the streamline. To apply this formula in our lab, we assume an ideal fluid that is steady, incompressible, frictionless, and moving along the single path. We test this using barimeter as fluid force its way through the narrow throat. The area drop, velocity peak, and our manometer tube will show a corresponding drop in static pressure. This is exact relationship in our lab data aim to verify.
Now, I will present the data analysis for our Bernoulli's experiment. First, I will explain the sample calculation used to analyze our experimental data. The first calculation is the cross-sectional area of each section of the tube. We obtained the diameter from the given dimensions on the apparatus and calculated the area using the equation A equal to pi d squared over 4. Next, we calculated the flow rate by dividing the volume of water collected by the time taken. After obtaining the flow rate, we calculated the velocity of the fluid at each section using the equation V equal to Q over A. And then, we calculated the velocity head using the formula V squared over 2g, where g is the acceleration due to gravity. Finally, we calculated the total head by adding the pressure head and the velocity head. These calculations were repeated for all 6 tubes in each of the 3 experimental tests. Since there were many calculations involved, we used Microsoft Excel to enter the formulas and automatically calculated all the values. This helped us in making the calculation process faster and more organized.
Moving on to our discussion, our data clearly validates Bernoulli's principle. As water moved from wider tube 1 to narrower tube 5, its velocity significantly increased, causing pressure head to drop. We also noticed that the total head steadily decreased across the system. This happens because of energy loss caused by friction and fluid turbulence, which is expected in real-world dynamics. To improve the accuracy of future trials, we have a few key recommendations. First, we must ensure the equipment is perfectly level to keep the elevation baseline uniform. Second, we need to completely bleed out any air bubbles in the manometers as they distort the pressure readings. Finally, for eye level readings, we need to look directly at the meniscus of water column to avoid parallax error.
To summarize everything up, this lab successfully demonstrates how Bernoulli equation govern real-world fluid dynamics. By analyzing water flowing through our venturi apparatus, we directly witness the trade-off between kinetic energy and pressure. Whenever the fluid velocity increases at the throat, the static pressure drops exactly as we predict in the theory. While our experimental data closely follow the ideal Bernoulli equation, our calculation of the total headline also highlight the reality of fluid mechanics, showing minor losses due to real-world friction and turbulence. However, this experiment confirmed that the despite ideal assumption like frictionless flow, Bernoulli principle remain a highly accurate and fundamental tool for engineering application, from designing piping network to understanding fluid behavior. Bye!